So let's get started. Our first presenter, Mark Wallace, has been with Semantic Arts, I believe, Mark, for 6 years, or is it 7 years?
It's getting on. It's actually not quite 6. It's like 5.5 right now.
Gotcha. Okay. Yeah. And Mark brings a unique software engineering background coupled with ontology modeling experience. And he'll be speaking about the tight alignment between FAIR and data-centric principles with a follow-on demonstration. So whenever you're ready, Mark.
Yeah, thanks, Steve. All right, and we'll get started. We're going to talk about FAIR for free with data-centricity. And of course, this is in conjunction with the Data-Centric Architecture Symposium. And my understanding is the audience, they kind of been through all that. They understand what data-centricity is. So I want to talk a little bit about how you get FAIR data for free. So FAIR data was an idea that was kind of first put out by the publication Scientific Data in 2016. And it was a set of guidelines to improve 4 things about data, really. And that's what FAIR stands for, right? Findability, accessibility, interoperability, and reuse of digital assets. And there was an emphasis on machine actionability. So if you go and read up on GoFair, I've got a link there. It's just go-fair.org. You'll see that they talk about machine accessibility a lot as part of what they're trying to do to make the data findable, accessible, interoperable, and reusable. So what I want to talk about today is essentially how you get FAIR data pretty much for free if you're doing a data-centric knowledge graph. That's what this talk will be about, how will a semantic knowledge graph help you become FAIR. So I want to level set. Maybe everyone knows this, but I want to talk about what do I mean when I say a semantic knowledge graph, because people talk about graphs and property graphs and things like that. So a semantic knowledge graph is a graph that's an RDF graph. RDF is the Resource Description Framework. It's been a standard since 1999, actually, from the World Wide Web Consortium. It's an RDF graph with an OWL ontology as its schema. So we can kind of see from the little layer cake here, there's a set of technologies that have made semantic knowledge graphs possible. There's basically, Unicode or standard characters, and there's the notion of the URI, which is, of course, the way we get around the web for the most part. Everything's done with URI, which is a universal resource identifier. And most of these are URLs, which is a universal resource locator. So you can actually click in a browser and get somewhere. So that was kind of already there. Then, forgive me, I'm biting off a cold. XML and XML schema and namespaces were a next layer that people started to get in to make data accessible and more readable by humans, but also machine processable. And then on top of that, we get to RDF, which is the Resource Descriptor Framework, which allows you to make graphs using URLs. And then something called RDF Schema, which adds a little more information to those graphs. It allows you to state that things are members of a certain class, meaning they're a type of thing, like a piece of equipment or a car or a person. It also allows you to find properties, and actually something interesting, a hierarchy of properties, meaning you can have more specific and more general properties. Like I could have a general property has parent, and I could have a more specific property has father, and I could actually link those together and say one is more general than the other. And then we move on to ontologies, which is basically OWL. That's the ontology web language. And that gives a much richer way of describing the things you're talking about in the graph. Much more rigorous and formal logic and much more richness than just sub-property or subclass. You can begin to say a lot of other things like, how do you know something's a member of a class? It has these kind of properties to these kind of entities, things like that. As most of you probably know from the symposium or from reading Dave McComb's books, a semantic knowledge graph is the heart of the data-centric architecture. I've got a little plug there for his book, The Data-Centric Revolution. I'm hoping many of you have read that. But given this technology stack, this RDF and OWL ontology, it really makes the data-centric architecture possible. Excuse me. And one of the key takeaways for a semantic knowledge graph is that it uses URIs for its schema, which means it's describing its vocabulary of the graph with URIs. And it uses URIs for the data. So each entity in the graph gets a URI as its identifier. And the real key to that is it means that your schema, your types and properties, and your data are web scale. They're global in scale. You know, as opposed to things like property graphs where things are kind of memory scale. Like there's no provision to make the IDs actually be resolvable globally and not conflict with other people's IDs globally. But the RDF was built from the start explicitly to have that level of scope. And that really is why we're able to get FAIR from it. And I hope that'll become clear as I go along. So the next thing we're going to do is we're going to do pretty much a tour of FAIR and the 4 letters of FAIR, the F, A, the I, R. We're going to go through each of those in turn and kind of just emphasize and show how each of these is giving you, or the semantic knowledge graph is giving you FAIR for free. In fact, in this picture on the side, which is very small, if you go to the FAIR website, that gofair.org, you will see they have a complete list, a breakout of FAIR into almost like sub-bullets of the F and sub-bullets of the A and so on. And so actually that's the way the rest of this talk will be structured. I'm going to go through each one. So let's start with findability. So according to the FAIR principles, findability means these things. It means that your data and your metadata are assigned globally unique and persistent identifiers. Well, keep that in mind. We just talked about identifiers. Your data is described with rich metadata. Your metadata is clearly and explicitly includes the identifier for the data they describe. So there's you can tell the data clearly indicates like what is its class, things like that. What properties is it using? And basically, the metadata is registered and searchable in a searchable resource. So let's talk about now the semantic knowledge graph that I just described. First off, all the data is in the graph, right? So there's one place that you can go look for things that makes it searchable and findable. And kind of huge emphasis, all the metadata is in the same graph. So when they talk about the metadata, the data is described with rich metadata. The metadata, this is F3, is clearly and explicitly tied to the data they describe. In a semantic knowledge graph, all that stuff's in the same place, which is kind of different than, say, relational databases, right? You can use SQL to query the data, but you can't use SQL to get at the shape of the tables, the names of the tables, stuff like that. There's usually a different language for that sort of thing. The cool thing is, you know, the data and the metadata are all accessible in the same way. And as I say, they're all done with IRIs, which means they already have those unique identifiers. And one of the keys is to make them persistent. That's not built into an identifier. You could create a URI and make it gone tomorrow. But one of the tenets of building these kind of graphs is persistent URIs, so that people can go find that entity a year from now. This point is just saying, you know, the nice thing is you can access the data and the metadata in the same query because they're all triples when it comes down to it, all RDF triples. So that's it in terms of the findability. I want to now go on to accessibility. So the tenets of FAIR are saying that all metadata are retrievable by their identifiers using a standard protocol. The protocol is open, it's free, it's universally implementable. The protocol allows for authentication and authorization, and the metadata should be accessible even when the data is no longer available. I'm a little confused on that A2. I'm not sure I totally get that one, but we will talk about that, the way I think of that in the context of semantic knowledge graphs. So first off, we use, talking about standard identifiers and using a standard protocol. Remember, we use URIs for all the data and the metadata. And actually, part of this, one of the standards in this stack is called Sparkle, and it stands for, it actually stands for Sparkle Protocol and RDF Query Language. So a lot of times, if people are familiar with the idea of Sparkle, they tend to think of it as the language by which you query the data, and it is, and it's a standard language, which is part of what the fair accessibility part wants. But remember, that second letter is actually protocol. So it's actually a standard, open, and secure protocol. In addition to the language that you use to query things, it's a standard protocol. So there we're meeting that standardized communication protocol. The protocol is open and free and universally implementable. That's true because it's not a proprietary thing. It was built by the World Wide Web Consortium, and there's specifications out there for it. And lots of companies have built Sparkle engines to query their RDF stores. The protocol allows for authentication and authorization. It basically works over HTTP and RESTful APIs, and that includes HTTPS, so the secure protocols. So basically, it's just a standard web communication as part of the standard. Therefore, I can go right now, for example, and query something called DBpedia, which is all of Wikipedia's data, or a good chunk of Wikipedia's data, put into an RDF form. And because it's a standard protocol, I don't need to pre-communicate with the people at DBpedia and say, hey, can you give me access, and can you tell me how your API works? I can just use that standard protocol to get in there and query the data. That last one, A2, metadata should be accessible even when the data is no longer available. The way I take that to mean is, again, we use OWL ontologies for metadata. We have knowledge about, we put in knowledge about the schema, which I think of as the metadata. When the data is no longer available, you still have access to the ontologies. They may also mean the idea of, if you delete a piece of data, can you still know that it existed at one time? And there are ways to do that. There's multiple ways to do something called provenance, which means you can, there are ways to say there was a statement that was this at this time, and here's when it was deleted. I'm not going to get into that now, but those are my two interpretations of A2. The next part of FAIR is the idea of interoperability. So the FAIR guidance says that the data and the metadata use a formal, accessible, shared, and broadly applicable language for knowledge representation. You may recognize that's going to be OWL, which is formal, it's shared. Again, it's an open standard that's not proprietary, and it allows very rich representation. Metadata use vocabularies that follow the FAIR principles. So we'd like to be able to use other vocabularies that also are accessible and interoperable and findable. And your metadata and data can include references to other metadata. So as I mentioned, for point one, we're using a very formal modeling language, OWL, when we're doing a semantic knowledge graph. So it is a broadly applicable language. You can model, we've modeled all sorts of things in it. It is formal. Again, it allows you to define axioms and things that can be operated on by automated reasoners to actually infer new facts. It's actually that formal. It's also, that formality also allows you to find errors in your data as well. Again, they mentioned it being shareable. Remember, OWL models are globally shareable because they use IRIs or URIs for all their concepts. So different organizations can define concepts, different standards bodies, and other people can use them and never worry about, I'm confusing my model of a digital twin versus someone else's. I can say, I want to use Siemens model for digital twin. I'll use their full IRI. Everyone will know what I'm talking about. There'll be no confusion. And models are globally composable. This gets into that idea of making references to other metadata. So here's like, for example, I can use an ontology. For example, we have something called GIST. So we've made an ontology, Semantic Arts has, that we share with the community. And I can have GIST then go out and use some of the SCOS ontology, which is a simple knowledge organization standard. And I'm essentially composing, and I'm saying part of my ontology is what Semantic Arts has defined for these concepts, and then part of mine is what SCOS does for taxonomies. And then maybe I want to use, I don't know, owl time or some other ontology that goes out and talks about time structures. So because these are all IRI based, and because you have the ability within OWL to say, I want to import this ontology from over here and that from over there, you actually can globally compose. That's a case of globally composing your metadata, what schemas you're going to use. And similarly, you can globally use data from all over the place. The whole linked open data world proves that you can have IRIs to represent things, and you can go out and pull that data into your models. Which kind of gets us to the last one, which is reuse. So the FAIR guidance says this about reuse. The metadata are richly described with a plurality of accurate and relevant attributes. So lots of attributes you can use to richly describe things. The data and metadata are released with a clear and accessible data usage license. The data are associated with detailed provenance, or kind of traceability as to where the data came from. And that the data can meet domain relevant community standards. So let's look at these. First off, with OWL ontologies, there is a very rich set of axioms and annotations. By axioms, I mean the formal things that let you say, you're this kind, you're in this class of things if you're, let me use an example. You're a parent if you're a human and you have at least one child. So you can, some of that rich metadata to describe what we mean when we say a parent would be like that. We can use those sort of things and give a logical description of what would make you one of these things. There's also a lot of rich annotations. There's ways to say this concept has this preferred label in this language and this preferred label in this other language, and then it has alternate labels in these different languages. You can annotate things with a definition, a textual definition. You can give them history notes. You can just do all kinds of things to give very, very rich metadata to any of the concepts or the data that you're talking about. All of these can attach to any IRI at the schema or data level. You can certainly license your models and data. Many ontologies are kind of open license. We have I think the Creative Commons license for GIST. So the point is you can associate any of the standard licenses that you see in the software world out there with your data and or your ontologies or your schemas. There are many provenance options. There's the idea of triple level provenance. That's where every little statement you make, I don't know if I've said the word triple yet in this talk, but all of this boils down to, in these graphs, to triple write a node, an edge, and a node, or a subject predicate object. So some people get to where you can put provenance on every little one of those atoms or statements. This came from here, this came from here. This statement we have 75% confidence in, et cetera, et cetera. So that's one option. There's another option called Probo, which is, again, a W3C standard ontology for provenance. It's more at the entity level. So instead of thinking about little statements, you're thinking, I've got an entity, the Mark Wallace who lives in Melbourne, Florida, an entity about a person. And you could say, I have this data on Mark, and it came out of the census data from 2020, and it was put into the system on this date, et cetera. So you're kind of all hanging off that Mark Wallace node, and you'd be putting all kinds of provenance on that, but not necessarily down to each triple about me, but just saying this entity, here's some things I know about them and where it came from. Also, again, in this idea of being able to use domain relevant community standards, there's the notion of it's easy to incorporate other standards. One of the ones we use an awful lot is the idea of taxonomies. So these would be a hierarchical, semi-formal, well-curated organization schemes. And there's actually something out there called SCOS, which is a standard knowledge or organization scheme that is written in OWL, and we make use of this a lot. It allows you to essentially model the kind of things that most taxonomists model, right? Here's a set of terms. Here's the hierarchical way that these terms break out in terms of parent and child. This term is related to that one. So I'll give you an example. A tent and a camp stove. A tent is not a camp stove, and a camp stove is not a tent, but a camp stove is related to a tent. Just the people tend to relate those two objects. Whereas, a tent might be more narrow than a particular structure. You might say a house is a structure, a tent is a structure, skyscraper is a structure. So anyway, you can, with the SCOS scheme, you can define all kinds of those relationships, broader, narrower. You can link between two different schemes that maybe two organizations have come and have created and say this term in this scheme is a near match to that one or is an exact match to that one. So all of this reuse and this ability to reuse taxonomies and other things as all part of your modeling is all kind of comes with a semantic knowledge graph. All these standards are already there. Lastly, in terms of exchange formats, right? So not only do you have the standard taxonomies, but can you exchange these with other people? Sure. There's XML formats for this. There's JSON formats for this. There's something called Turtle, PTL, RDF Turtle, which I'll actually show you in a minute, formats. So you also have the ease of exchange, community standards against around the exchange of all this information. I see some questions coming up, and I'll definitely be doing some Q&A at the end. So thanks for those. The last thing that I want to talk about, because it's not really one of the letters, it's of FAIR. This is the other thing they always talk about, machine actionability. So they want all these things, but they want the machine to be able to do something where it's not just a human interpreting things. And so what's nice about semantic knowledge graphs that use RDF and OWL is that it's done in such a way that it provides easy understandability to not only humans, but also to machines. Meaning, for humans, the terms are pretty natural, and the structure is pretty natural. I'm showing just a little chunk of the RDF Turtle language here. And the first 4 bits, which don't look super understandable, maybe it's just this, and this is just a shorthand that allows you to get to an easier way of reading things and then still have things turn into IRIs in the machine. So these are just called namespace prefixes. But the main data part is here. And as you can see, this structure, even if you've never seen RDF Turtle in your life, is pretty understandable to the human. Okay, so what are we saying here? It looks like Mark has parent Lou. All right, it sounds like we're talking about a person. Mark has some parent whose name is Lou, or at least his identifier is that. Lou then has a parent who's Lou Sr., and then Lou Sr. has a parent that's William. I mean, I think anyone could say, what does this talk about? Well, it's kind of a generational genealogy. It looks like it's just labeling people and their parents. And you'd be right. So that's why I think it's pretty accessible to humans. But the cool thing is that machines can also reason over the information in a model when the data is depicted in RDF like this. So, for example, there's a couple other things now I could say in this data set. I could say, and again, the human, it's understandable to the human. I'll show you in a minute how it's understandable to the machine. But all this is saying is, hey, when we were saying these very simple statements, subject, predicate, object, it turns out that this has parent is actually a subproperty of has ancestor. So subproperty just means if this is true, then this is true, or this is a more specific case of that. In other words, if Mark has parent Lou, then it would also be true that Mark has ancestor Lou. Just saying, in the world, has parent would be a more specific case of has ancestor. If you have a parent, then they're also your ancestor. And then this little statement, you just are telling or declaring the fact that has ancestor is a transitive property. Now, if you go back to math class and remember what transitivity was, it just means if something holds from A to B and then it holds from B to C, if transitivity is the case in this world, then the same thing would happen from A to C. So if you have A to B and B to C by the same connection, you have A all the way to C by that same connection. So in other words, if I have an ancestor that's Lou and Lou is an ancestor that's Lou Senior, then I also have an ancestor that's Lou Senior. So it goes across the top of those properties and is true as you walk down the line. So again, declaratively, a human can pretty much understand this, but the machine can understand this too. Some examples of machine actionability are classifying things. Classifying things means you get a piece of data and you can kind of tell what bucket to put it in. Like I got this piece of data, I got a moving target on my radar, and I get a few other pieces of information. I'm able to say, wait, that's a tank versus that's an airplane or something like that, right? First, I know it's something moving, then I can start to classify it. I can say that someone is a parent, not just a human, if I know that they have children. The machine can actually work on these axioms and do that sort of thing. Understanding transitivity, I actually just talked about that, right? It knows that if A is a part of B and B is a part of C, then A is a part of C, right? So composition, maybe you would call that. The machine can act on that and figure out what are all the parts, even if not the first level down in the composition. There's even some machine actionability for discovering sameness. Let's say you have two entities in your graph you've gotten from different data sources. And then a combination of the axioms and the properties that you've stated would actually allow the system to merge the identities and say, oh, wait a minute, these two things that we've been tracking are actually the same thing. We call the main thing we use there something called functional properties. But this is just an example of a lot of the kind of machine actionability that you get when you model this way. And actually, the next thing I want to do is kind of go into a demo. So let's do that. I'm going to share a different item. For those of you who may not be familiar, I'm now sharing a tool called Protege. Protege is an open source ontology editor. And I've taken the data file that we really just talked about. Let me make this a little. That one that I showed you that says, Mark and Lou. Mark has parent Lou. Lou has parent Lou Senior. I've got a very simple ontology here. It just says organizations and people. I've got some individuals in here, Lou and Lou Senior and Mark and William. And I've said a few things about them. As we kind of saw, Mark has parent Lou. Lou has parent Lou Senior. Lou Senior has parent William. And then I've defined some properties over here. So I've said that there's such a property as has parent, and I've said it's a subproperty of has ancestor, which means if someone's your parent, they're also your ancestor. And then I've marked ancestor as a transitive property. So it's pretty much what I just showed you, that human readable stuff. I've just put this into a tool that will allow us to do the machine actionability. And what I'm going to do now is I'm just going to go up here and run a reasoner. And when I run the reasoner, I can start looking at things like, you'll notice now, and I can turn the reasoning on and off. So I had said Mark's parent was Lou. Because of the declarations I made, and because of its knowledge, all I said was Mark has parent Lou. That's all I said. Everything in yellow is what the reasoner figured out. It figured out that I must have an ancestor, that Lou is not just my parent, but my ancestor. And you can actually click here and you can see how it figured it out. It says, well, Mark has parent Lou, and has parent is a sub of has ancestor. So that must mean Mark has the ancestor. But if I go on, and say, okay, it also figured out that Lou Senior is my ancestor, and even William is my ancestor, which would be like my great-grandfather. And again, you can ask the reasoner, and it says, well, ancestor's transitive. Mark has parent Lou. Has parent is a sub of ancestor. Okay. So now we can start figuring out has ancestor. And then Lou had a parent, Lou Senior. Lou Senior had a parent, William. That's how I'm able to figure out that Mark must have an ancestor who is William. So that's one example of machine actionability. How are we doing on time? pretty good. I wanted to show you one more thing. I'm going to do this one kind of on the fly. But let's say, for example, we now want to do one of these things I call about axioms and classification. So pretty sure, yeah, I've said all of these are persons. Let's say I want to go in and say, all right, I am going to declare the notion of a parent. I'm going to make another class, like, and I'm going to say, you're a parent if you're a person. Actually, it's got a, I'll go ahead. It's pre-completing for me. You're a person. Well, I'll do it myself. And you have a has parent going the other direction. So in other words, there's the idea of has parent. So I declared that I have a parent. If I could have said has child also, I didn't do that in this example, but I'm just saying if you're a person and there's a has parent coming into the data. So for example, Lou has a has parent coming in from Mark. If you have a has parent that's some person, then you're a parent. It's basically just saying if you're the parent of someone, if you have a parent property, that just makes you a parent. Now that seems like totally normal to us because we use semantics as humans, right? Well, of course, if someone has a has parent relationship to me, that would make me a parent. But the system wouldn't know that, except I create an axiom that says, here's how you know what a parent is. And then if you refresh the reasoner, it actually figures out that Lou and Lou Sr. and William are all parents because they all had a case of someone, essentially, of them being the parent of some other bit in the data. So that's an example, again, of machine actionability. In the case of classifying things, I'm saying who's in the parent class, and I'm able to say, well, Lou's in the parent class. Why is Lou in the parent class? Because Mark has parent Lou, Mark's a person, Lou's a person, and we have this axiom that if you're a person and someone has parent coming into that node, then they're actually classified as a parent. I'm going to stop the demo there. I hope that kind of puts some reality to what I'm trying to say about this data is very, I think it's very human readable just to see what we call triples that are just in standard language, but also the idea that the machine can operate on that. And you don't get that in a database. You don't get that in a standard property graph. So getting back to just kind of wrapping up, in summary, what I'm trying to say is if you model your data using a semantic knowledge graph, which is basically RDF and OWL, then it's going to give you the findability, accessibility, interoperability, and reuse that the FAIR standard is talking about, and it'll give it to you with machine actionability, which basically means you will go FAIR if you just basically embrace the data-centric idea of semantic knowledge graphs for your data. And with that, I'll start taking questions. Can you explain slightly deeper how algorithms get configured or become embedded in a semantic model? Yeah, actually, let me talk about that a little bit because the semantic model, the standard of OWL is kind of a fixed set of axioms. So you may have seen me use, let's see, go back to this window real quick. If you look at this place here, there's a language, there's a set of constructs in OWL, like this is called a sum values from restriction. There's things like has value restrictions, which means if something like you could say a red wine is something that's a wine that has the color red. Now, I know that sounds, again, trivial, but actually a database isn't going to know that, but in OWL, you could say this. And now you're saying, instead of this says it has this relationship to something that's in this class, a has value relationship says it has a relationship to this particular individual. So maybe something is something if it's under, has parent organization, IRS or something. So you can use a specific individual, not a class. There's a whole set of these axioms. I'm going to just spitball it and say there's about 30 different constructs that you get in the OWL DL language. You could look up the OWL spec and see all the properties it has. Functional properties, inverse functional properties, like I said, has value relations, cardinality relations, meaning, less than 1, greater than 1, exactly 3. And they just are what they are. So the point is, if those are useful in your modeling and the idea is they were intended to be useful in modeling, you have those rules by simply using those different properties. Now, then there's some technologies that go beyond the OWL standard. There's something called SWRL, which is Semantic Web Rule Language, SWRL. That lets you write in RDF and OWL in RDF form. So within your own graph, you could define rules that go beyond that. You could define the uncle rule, or you could, define, you could just define different rules that aren't the fixed set of things that OWL DL gives you. And then beyond that, so SWRL is pretty standard. A lot of, it's an open standard that's out there that people can implement, and a fair number of reasoning stores use it. And then sometimes you'll find individual products will define their own rule languages as well. So hopefully that's an idea of, for straight OWL, for pure OWL, you will utilize the different axioms that are available in the OWL standard. If you want to customize rules, you can use something like SWRL.
Yeah, Mark, if you have any other final comments, we'll just move on to the next presenter.
Okay. I mean, all I can say is, like, I was not as aware of the FAIR standard. I've been doing OWL stuff since 2004 in ontologies and knowledge graphs. When we had a client that wanted us to address FAIR, and FAIR was important to them, and I went to read the standard, I was like, this must have been a semantic web guy. I mean, I don't know if it's a guy or a bunch of people, but when I looked at what they're looking for, not only did I see the semantic web stack through and through, but I couldn't think of an alternative. I thought, if you want all of these things, you'd have to reinvent the semantic web stack. You know what I mean? So to me, it almost seemed like the fix is in, right? Like FAIR, whoever did FAIR is like, they got to be thinking, once you read FAIR, you're like, how would I do this without RDF and L? I don't know how else I would do it, or at least RDF and RDFS. I'll make a quick statement on that. And this even goes back a little bit to the notion of the linked open data that Peter Campbell was talking about. A lot of people find OWL a little too complex or too rigorous or whatever, and they don't want to mess with it. I mentioned in my little layer cake stack that I showed in one of my slides that there's something called RDF schema. It's also called RDFS, which is a lighter weight. That's the one that just says, look, we're going to have types for things, and we're going to have the ability to define a hierarchy of things, right? Like, a dog is a mammal, is an animal, is a living thing, right? So you can have these classes of things and understand the generality of the specific. You can also do that with properties, like has mother is a subproperty of has parent, is a subproperty of has ancestor. These things that we take for granted semantically in our minds all the time, but you can say those very easily. All of those are just done with the RDFS standard. And you'll see a lot of linked open data that uses those terms. They'll say RDFS, this is an RDFS class, which is like, again, parent or human, or RDFS property. And so some people don't get into the tighter, more owlish ways of doing things. And you're still getting IRIs for your schema, your IRIs for your data, a shareable standard. You're still getting the Sparkle protocol for querying things. And over the web. So there's kind of different levels that you can go on this if you don't want to get too logical or too axiomatic in the way you do things.
Well, that's really good to know, Mark, because I think there's a level of adoption that we tend to in the community struggle with. So there's ways that people can move into things and take baby steps along the way. Yep. as they learn.
Exactly. Yep.
All right. Well, thank you again, Mark. Appreciate it.
All right. My pleasure.